In question 8 of this exercise, we have this figure 10.12 in which a quadrilateral ABCD is drawn to circumscribe a circle. Circumscribe means that all the four sides of the quadrilateral, they touch the circle inside it. So we have to prove that AB plus CD is equal to AD plus BC. So we basically have to prove that the opposite sides of the quadrilateral have the same sum. So AB and the opposite side CD, they have the same sum as AD and the opposite side BC. Okay, so the logic to solve this problem is actually very simple. It is based on the fact that the tangents drawn from any external point to a circle, the two tangents drawn from any external point to a circle, they will have the same length. So this means that in this figure, AP and AS will have the same length. So let me highlight AP and AS. So AP is this segment and AS is this segment. They have the same length because both of these are tangents drawn from A to the circle, right? And then similarly, if we consider BP and BQ, they will have the same length. So BP is this segment and BQ is this segment that I'm highlighting. So BP and BQ will have the same length for the same reason that they are the tangents drawn from B to the circle. Then CQ and CR, they will have the same length also, correct? So CQ and CR will have the same length, and similarly DR and DS. So DR is this segment, DS is this segment, they will have the same length. Now if you consider AB, this segment, and CD, which is this segment, and if you observe the parts in these two segments, so you have AP, BP, CR and DR, and then if you consider the segment, the side AD, and if you consider the side BC, they have the segments, they have the parts AS, DS, BQ and CQ. So it's easy to see that the two pairs, they have the same parts. So the first pair is AB and CD, opposite side CD, and the second pair is AD and the opposite side BC, correct? So in the first pair we have AP, and correspondingly in the second pair we have AS. Then similarly in the first pair we have BP, and correspondingly in the second pair we have BQ. Then in the first pair we have CR, and in the second pair we have CQ, and in the first pair we have DR, and in the second pair we have DS. So basically the parts in the two pairs are the same, so the sum of the two pairs will be the same. So this is the simple logic that we can use to solve this problem. Okay, now let's write out the proof properly. So as I said, we are making use of the fact that the tangents drawn to a circle from any external point, the tangents are equal. Okay, so this means that AP is equal to AS. So these are the two red segments that are highlighted in the figure. Then BP is equal to BQ. These are the two green segments. Then CR is equal to CQ. These are the two pink segments. And then DR is equal to DS. So these are the two dark blue segments that are highlighted. Okay, now let's call these equalities 1, 2, 3 and 4. And now we're going to simply add these four equalities. Okay, so by 1 plus 2 plus 3 plus 4, so what will we get on the left side if we add these four equalities? So AP and BP will give us AB, and CR and DR will give us CD, correct? So on the left side we will get AB plus CD, and on the right side we have AS and DS, so this will give us AD, and BQ and CQ together will give us BC. So on the right side we will get AD plus BC, and this is what we had to prove, that AB plus CD is equal to AD plus BC. So this is actually an important result from circles, that if you have a quadrilateral circumscribing a circle, then the opposite sides of the quadrilateral, the two pairs of opposite sides, they will have the same sum. Just like in this case, AB and the opposite side CD have the same sum as AD and the opposite side BC. Okay, so this completes our proof for question number 8. Question 9 of this exercise says, in figure 10.13 that you see here, xy and x dash y dash are two parallel tangents to a circle with center O. So if you see this figure, you see that there is a circle in the figure. This point O is the center of that circle, and xy, this line here, and x dash y dash, this line here, these two lines are parallel tangents to the circle. And another tangent AB with point of contact C intersecting xy at A and x dash y dash at B. So this segment here, AB, this is also a tangent to the circle. The point of contact of this tangent is C, this point here, and this tangent intersects xy at A, this point, and x dash y dash at B. Now we have to prove that angle AOB is equal to 90 degrees. So this angle here, angle AOB, which is subtended by the tangent AB at the center O of the circle, we have to show that this angle is equal to 90 degrees. The proof is actually quite simple, and to understand the proof, let's first join the center O with the point of contact C. Okay, now if you compare triangle OAP with triangle OAC, it's easy to show that these two triangles are congruent, and therefore this angle OAP or angle PAO will be equal to angle CAO, this angle here, correct? Similarly, it's easy to show that the triangle OBQ is congruent to triangle OBC, and therefore the angle QBO, which is this angle QBO, is equal to angle CBO, which is this angle here, right? And now if you look at the angles PAC and QBC, so observe these angles carefully in the figure. Angle PAC is this entire angle, and angle QBC is this entire angle. What do you think is the relationship between these two angles? Well, the sum of these angles is equal to 180 degrees because these are co-interior angles, and therefore the half of their sum will be equal to 90 degrees. But what is the half of their sum? So if you take half of angle PAC, you get angle OAC, which is this angle, and if you take half of angle QBC, you get angle OBC, which is this angle. So OAC and OBC add up to 90 degrees, and from there, using the angle sum property, it follows that this angle must also be equal to 90 degrees. So this is the proof. It's very simple. Now let me write it out for you step by step. Okay, so as I said, we will begin by comparing triangle OAP with triangle OAC. So I'm directly going to make use of the fact that these two triangles are congruent. It's very easy to show. If you want, you can pause the video for a few moments and think about how you can show that these two triangles are congruent. But I'm going to use this result directly, that triangle OAP will be congruent to triangle OAC. And from here, it follows that angle PAO PAO is equal to angle CAO. So angle PAO, this angle here, is equal to angle CAO, and let's call both of these angles angle 1. Okay, so angle PAO and angle CAO is equal to angle 1. Now let's compare triangle OBQ, this triangle, with triangle OBC. Again, these two triangles are congruent. I'm going to make use of this fact directly. If you want, you can pause the video and think about how to show that these two triangles are congruent. So triangle OBQ is congruent to triangle OBC, and from here it follows that angle QBO is equal to angle CBO. Correct? So angle QBO is this angle, angle CBO is this angle. These two angles must also be equal. So let's call these two angles angle 2. Alright. So both these angles are equal to angle 2. Now because xy and x dash y dash, they are parallel, it follows that this angle PAC, this whole angle, plus this whole angle QBC, their sum must be equal to 180 degrees. So let's write this. Since xy is parallel to x dash y dash, it follows that angle PAC plus angle QBC, this is equal to 180 degrees. And why is that? Well, simply because these two angles form a pair of co-interior angles. Okay, and this means that if you multiply both sides by half now, so half of angle PAC plus half of angle QBC, this will be equal to half of 180 or 90 degrees. But what is half of angle PAC? Well, this is simply equal to angle 1, this angle here, half of angle PAC. And what is half of angle QBC? This is simply angle 2. Correct? So now we can write angle 1 plus angle 2 is equal to 90 degrees. Now I want you to think about the triangle OAB. I'm going to highlight this triangle for you, triangle OAB. Okay, in this triangle, two of the angles are angle 1 and angle 2, and we have just shown that their sum is 90 degrees. And from here it follows that the third angle, which is the angle whose measure we want to find, which is angle AOB, it follows that the measure of angle AOB will also be 90 degrees. So let's write this. In triangle AOB, the triangle that I've highlighted, angle AOB will be equal to 180 degrees minus the sum of the other two angles, so angle 1 plus angle 2, and this basically follows from the angle sum property. So this is 180 minus angle 1 plus angle 2 is 90 degrees. So 180 minus 90 is 90. So we have proven that the measure of angle AOB is 90 degrees. Okay, this is what we had to prove. So this completes question number. Question 10 says, prove that the angle between the two tangents drawn from an external point to a circle is supplementary to the angle subtended by the line segment joining the points of contact at the center. So this is a long statement, and to understand what this statement really means, let's draw a figure. So here's an arbitrary circle that I have drawn. Now let's say that this point here is the center of the circle, so let's call it O. Now we have to take two tangents drawn from an external point. So let's take an external point anywhere outside the circle. So let's take this point P, and from the point P, let's draw two tangents to the circle. Okay, so one tangent would be something like this, and the second tangent would be something like this, right? And the points of contact, let's call them A and B. Now let's see with respect to this figure, let's read the statement again. So prove that the angle between the two tangents, so the angle between the two tangents is this angle here, right? Prove that this angle is supplementary to the angle subtended by the line segment joining the points of contact. So the line segment joining the points of contact would be the segment AB. So if we join AB, this segment, and the angle subtended by this segment at the center. So to get that angle, let's join A and O and B and O like this, correct? And now we see that AB, the line segment AB, subtends this angle, angle AOB at the center. So these are the two angles being talked about in the problem statement, and we have to show that these two angles are supplementary. In other words, we have to show that their sum is equal to 180 degrees. Okay, so this is actually a very straightforward problem. All we need to do is make use of the fact that this angle OAP, this will be 90 degrees because the radius through the point of contact is perpendicular to the tangent, we know that. And this angle, similarly, angle OBP, this angle will also be equal to 90 degrees. And therefore, if you consider quadrilateral OAPB as a whole, OAPB, the sum of the four angles in the quadrilateral must be 360. And of those four angles, two angles sum to 180 degrees. Angle OAP and angle OBP, they will sum to 180 degrees. So the remaining two angles, which are angle P and angle O, they will also have a sum of 180 degrees. So this is the logic that we are going to use. Now let's quickly write out the solution step by step. So let's start by observing that because AP is a tangent at A, so OA will be perpendicular to PA, and similarly OB will be perpendicular to PB, correct? So this means that angle OAP is equal to 90 degrees and OB perpendicular to PB means that angle OBP is equal to 90 degrees. Okay, now in the quadrilateral OAPB, okay, in this quadrilateral OAPB, let me actually highlight this quadrilateral. So OAPB, this is the quadrilateral I am talking about. In this quadrilateral, the sum of the four angles must be equal to 180 degrees. And what are the four angles? So angle P is one angle, this angle here. Then angle OAP is one angle, which is this angle here. Then angle O is the third angle, this angle. And then an angle OBP is the fourth angle. So angle OBP. The sum of these four angles must be 360 degrees. This is the angle sum property for quadrilaterals. Okay, so angle P and angle O, we leave them as it is. And then angle OAP, instead of angle OAP, we write 90 degrees. And instead of angle OBP also, we write 90 degrees. Okay, so this sum is equal to 360 degrees. Okay, now we can combine this 90 and 90, so that will give us 180. So angle P plus angle O plus 180 degrees is equal to 360 degrees, and therefore angle P plus angle O will be 360 degrees minus, you take this 180 to the right side, so 360 minus 180 degrees or 180 degrees. So we basically had to show that angle P and angle O are supplementary. In other words, their sum is 180 degrees. So therefore, we have completed our proof. Okay, and this completes question. Question 11 says, prove that the parallelogram circumscribing a circle is a rhombus. So here's a circle that I'm going to use to draw a figure for this problem. And now we have to draw a parallelogram that circumscribes this circle, which means that all the four sides of the parallelogram should touch this circle and the circle should be inside the parallelogram. So how do we draw such a parallelogram? So it's quite easy. First, draw any two tangents to the circle. So let's say this line here is one tangent, and then let's draw another tangent, let's say like this. Okay, and now let's draw two more tangents which are parallel to these two tangents. Okay, so I'm going to take a line that's parallel to the first tangent like this, right? Okay, to just touch the circle. And now let's take another line that's parallel to the second line that we drew like this. So now you have a parallelogram circumscribing the circle. So I hope you've understood how I drew this figure. I just first drew two tangents, any two tangents, and then I drew two more lines which were parallel to those two tangents and touching the circle. So this is how you can draw a parallelogram circumscribing a circle. Okay, now let's label the various points. So let's say that this is point A, and this here is point B, this vertex. Then this here is point C, and let's call this point here point D. So our parallelogram is ABCD, in which AB is parallel to DC and AD is parallel to BC. Correct? Now let's also label the points of contact. So let's call this here point P, and this point here let's call it point Q, and this point here let's call it point R, and then let's call this point here point S. Now we have to show that ABCD is a rhombus, which basically means that the four sides of ABCD must be equal. So we are going to use a result which we proved in question 8 of this exercise, which basically tells us that if you have a quadrilateral, if you have any quadrilateral circumscribing a circle, then its opposite sides will have the same sum. So let me show you, let me just recap that result quickly for you. Okay, so here in this figure we have a quadrilateral ABCD which is circumscribing the circle that you see, which basically means that all sides of the quadrilateral, they touch the circle. And we proved in question 8 that in any such situation, the quadrilateral, the opposite sides will have the same sum, which means that AB plus CD will be equal to AD plus BC. So let me write this for you. AB plus the opposite side CD will be equal to AD plus the opposite side BC. And this is what we proved in question 8. And for our proof, we made use of the fact that tangents drawn from an external point to any circle, they are equal. So for example, this tangent here will be equal to this segment here, and so on. So you can go back to the video for question number 8 and rewatch it if you have to, but I'm going to use this result directly for the current question. Alright, so I'm going to make use of the fact that for the parallelogram ABCD in our figure, AB plus CD will be equal to AD plus BC. Okay, and the reason is basically that we have shown this earlier in question number 8. But if this question comes up on an exam, you will have to write the proof of this thing completely. Okay, so you will have to first show that AB plus CD will be equal to AD plus BC. Now, because ABCD is a parallelogram, we also know that AB is equal to the opposite side CD and AD is equal to the opposite side BC. Correct? And this is simply because ABCD is a parallelogram. So if we make use of this fact in this relationship that we have written, so instead of AB plus CD, we can write AB plus AB. So instead of CD, I'm writing AB. And similarly on the right side, I can write AD plus, instead of BC, I can write AD again. Okay, so this gives me twice of AB is equal to twice of AD, and then we just cancel out the 2's on both sides, and we get AB is equal to AD. So the adjacent sides AB and AD in the parallelogram ABCD are equal, and this means that all four sides are equal. In other words, ABCD is a rhombus. A rhombus is a parallelogram in which all four sides are equal. So ABCD is a rhombus. Okay, so this is what we had to prove. So this completes our proof for question number. Question 12 is one of the most interesting questions of this exercise. Here's what it says. We are given this figure 10.14, and the problem statement says a triangle ABC is drawn to circumscribe a circle of radius 4 centimeters. So if you see the figure, you see that we have this circle here with the center O, and triangle ABC circumscribes this circle, which means that all the three sides of triangle ABC, they touch this circle, and one of the points of contact is this point D here. Okay, such that the segments BD and DC, into which BC is divided by the point of contact D, are of lengths 8 centimeter and 6 centimeter respectively. So we can see that BD is 8 centimeters and CD or DC is 6 centimeters. Using this information, we have to find the sides AB and AC. Okay, so we have to find the length of this side AB and the length of this side AC of the triangle. So the solution is a little bit complicated. So to understand the solution, let's first understand the figure in a better way. Okay, so we have this circle, and triangle ABC is circumscribing the circle. One of the points of contact is D. We can see that there are two other points of contact. Let's label them. So let's say that this point of contact is E, and let's call this point of contact as point F. Now if you join O with E and if you join O with F, what will be the length of OE and what will be the length of OF? Well, OE and OF are also radii of the same circle, and we are given that the radius is 4 centimeter. So OD, OE and OF, all three will have the same length, 4 centimeters. So OD is 4 centimeters, OE is 4 centimeters, and OF is also 4 centimeters. Now, using the fact that the radius through the point of contact is perpendicular to the tangent, we can also say that OD will be perpendicular to BC. So OD will be perpendicular to BC, OE will be perpendicular to AB, and OF will be perpendicular to AC. Correct? Okay. Now let's make use of the fact that if you draw two tangents from an external point to a circle, then those two tangents must be equal. So if you look at the point B, this point B is an external point for the circle, and from this point two tangents have been drawn to the circle. So BD and BE, and the length of BD is known. The length of BD is 8 centimeter, and this means therefore that the length of BE will also be 8 centimeters. And similarly, if you look at the two tangents from C, the point C to the circle, the two tangents are CD and CF, and therefore these two will also be equal. So CF will also be equal to 6 centimeters. Okay, so let's write these observations. So BD is equal to, so BE is equal to BD, and CF is equal to CD. And this is because tangents drawn from an external point to a circle have equal lengths. So BE equal to BD equal to 8 centimeter, and CF equal to CD equal to 6 centimeters. Okay, now our objective is to find the total length of AB and the total length of AC. So if you look at AB, AB is made up of two parts. You have AE and you have BE. But the length of BE is known to us. The length of BE is 8 centimeter, but we don't know the length of AE. Similarly, if you look at AC, in AC we have two parts, AF and FC, and the length of FC is known, CF or FC, that's 6 centimeters, but the length of AF is not known. Okay, but we can see that AE and AF are the two tangents drawn from A to the circle. So we can say that AE and AF will be equal. So let's assume that both of these AE and AF, they have a length of R centimeters. Okay, so AE is R centimeters and AF is also R centimeters. So our objective is to find R. If we find R, we can easily find the lengths of AB and AC. Okay, so now here's what we are going to do to find the value of R. Here's the logic that we are going to apply. So follow me carefully because this is slightly complicated. So we are going to join the center O of the circle to the three vertices of the triangles. So O with A, then O with B, and O with C. Now we are going to write the area of triangle ABC, the whole triangle, in two different ways. First, we will write the area of triangle ABC by observing that ABC is made up of three smaller triangles: triangle BOC, triangle AOB, and triangle AOC. So if we calculate the areas of these three triangles, these three smaller triangles, and if we add those three areas, we will get the area of the entire triangle ABC. So that's one way to write the area of the entire triangle. The other way is to apply the Heron's formula to the entire triangle ABC and calculate its area. So we will write the area in two different ways, and we will get two expressions for areas, for the area. Both the expressions will have R in them, the variable R. So we will equate those two expressions and we will get an equation in R, and solving that will give us the value of R. Okay, so that's the logic that we're going to follow. Now let's start. So let's first calculate the area of triangle ABC using the sub areas, the three smaller areas. Okay, so area. So let's calculate the area by adding the three sub areas. By sub areas, I mean the smaller areas, the three triangles that form triangle ABC. So we have triangle BOC. I'm highlighting this triangle in the figure. Observe it carefully. What is the area of triangle BOC? So if we take it to be half base into height, so we can write the area as half into BC into OD. And we can do that because OD is perpendicular to BC. So OD can be taken as the altitude, as the height. So area of BOC is half into base, which is BC. So what is BC? The length of BC is BD plus CD, or 8 plus 6, or 14. So half into 14 into OD. OD is 4. So this is the area of BOC. So 14 by 2 is 7. 7 into 4 is 28. So the area of BOC is 28 centimeter square. Now let's find the area of AOB, this triangle that I'm highlighting. So area of AOB, again by using half into base into height. In this case, we take the base as AB and the height as OE, because OE is perpendicular to AB, right? So area of AOB can be written as half into, what's the base this time? AB. So AB is made up of two parts. There is BE, which is 8 centimeter, and there is AE, which is R centimeters. So AB we can write as 8 plus R centimeters. Okay, so 8 plus R centimeters into OE we know is 4 centimeters. Okay, now this product is 4 by 2 is 2, and 2 into 8 plus R will be 16 plus 2R. So area of AOB will be 16 plus 2R, these many centimeter square. Okay, now similarly, let's find the area of triangle AOC, the third part of the whole triangle. So the area of triangle AOC, again we apply half into base into height. So this time the base is AC, and we can see that AC will be how much? 6 plus R. So FC is 6 and AF is R. So AC is 6 plus R centimeters. So 6 plus R centimeters into the height is OF, which we know is 4 centimeters, right? And now this product is 4 by 2. So that's 2. 2 into 6 plus R is 12 plus 2R. So we get 12 plus 2R centimeter square. And now finally, we can find the area of the entire triangle by adding these three areas, the area of BOC, of AOB, and of AOC. So the area of triangle ABC, the entire triangle, will be the sum of the three smaller areas. What are the three smaller areas? So we have 28 centimeters square, we have 16 plus 2R centimeter square, and we have 12 plus 2R centimeter square. So if we sum all of these, we will get the first area is 28, then we have 16 plus 2R, and then we have 12 plus 2R. So these many centimeter square. Now let's simplify this sum. So 28 plus 16 is 44, 44 plus 12 is 56, and then we have 2R and 2R, that's 4R. So we will get 56 plus 4R centimeter square. So this is one expression for the area of triangle ABC. Now let's calculate the area, the same area of triangle ABC using the Heron's formula. Alright, so now we are going to apply the Heron's formula. Okay, so area by the Heron's formula. And to apply this formula, remember that we have to calculate the semi-perimeter, the S, the value of S for the triangle. And how do we calculate the semi-perimeter? Well, we simply add the three sides and take half of that. So S will be equal, the semi-perimeter S will be equal to half of AB plus BC plus CA, correct? Now let's plug in the values. So half of AB is, how much is AB? So AB is 8 plus R, then BC is 14, and then CA is 6 plus R. So the semi-perimeter will be these many centimeters. So let's simplify this. So half into, then we have 8 plus 14 is 22, 22 plus 6 is 28, and then we have R and R, that's 2R. So half into 28 plus 2R, these many centimeters. So if we divide, if we multiply by half, we will get 14 plus R. So 14 plus R centimeters is the semi-perimeter. Now we have to calculate the semi-perimeter minus each side. So basically S minus A, S minus B, and S minus C. So S minus A will be, so the side A, the side with length A, we can take as BC. So S minus A can be 14 plus R minus, BC has a length of 14. So 14 plus R minus 14 centimeters, and 14 and 14 cancels out, so we are left with only R. So S minus A is R centimeters. Now let's calculate S minus B, where we can take B to be the side opposite vertex B or the side AC. Okay, so S minus B will be 14 plus R, which is S minus AC. AC is how much? AC is 6 plus R. So we have minus 6 plus R, or minus 6 minus R. So this is how we will write this. So these many centimeters, correct? So the r and minus r cancel out, so we have 14 minus 6, so this is equal to 8 centimeters. And then finally we calculate s minus c, and c will be the side opposite the vertex c, which is AB. So s minus c will be 14 plus r, which is the value of s, minus c, or the length of AB. The length of AB is 8 plus r. So we subtract 8 plus r, so we get 8 minus r. So 14 plus r minus 8 minus r centimeters. And again r and minus r cancel out, and we have 14 minus 8, which is equal to 6 centimeters. Okay, so now we have all the values that we need to find, to apply the Heron's formula. We have the value of s, we have s minus a, we have s minus b, and we have s minus c. Now let's apply the Heron's formula. What is the Heron's formula? Do you remember it? So the area, let's represent it by delta. The area is given by s into s minus a into s minus b into s minus c, and we take the square root of this product. So this is the Heron's formula. So let's plug in the values. So we have, instead of s we write 14 plus r, instead of s minus a we write r, instead of s minus b we write 8, and instead of s minus c we write 6. So the square root of this product and these many centimeters square would be the area. Now if you observe the product, you have 8 into 6, that's 48. 48 can be written as 16 into 3, right? 48 can be written as 16 into 3. So if you take the square root of 16, you will get 4. So I can bring out a 4 outside the square root, and then inside the square root I will be left with 3. Then I will be left with r and 14 plus r. So inside the square root I will have 3r times 14 plus r and then centimeters square. So make sure that you've understood this calculation properly. If you want, you can pause the video for a few moments and confirm that this is correct. Okay, so now we have obtained a second expression for the area by applying the Heron's formula. Now, as we discussed, all that remains to be done is to compare the two expressions for the areas. The first expression was 56 plus 4r centimeter square. So let me highlight this expression, 56 plus 4r centimeter square. And the second expression we have obtained is 4 times root of 3r times 14 plus r, these many centimeters square. So now let's equate these two expressions. Okay, so doing that will give us, the first expression is 56 plus 4r, and the second expression is 4 times root of 3r times 14 plus r. So now we have an equation in r, and now we can solve it and find the value of r. So the first step is to divide both sides of the equation by 4, because the left side is also perfectly divisible by 4. So this will give us 14 plus r on the left side, and on the right side it will give us root of 3r times 14 plus r. Now let's take the squares on both sides. So we will get 14 plus r whole square is equal to 3r times 14 plus r. Now we have 14 plus r square on the left side and we have 14 plus r on the right side. So do you think we can cancel them out on both sides? Well, we can cancel out a multiplier on both sides only if it is non-zero. But in this case, we can be sure that 14 plus r is non-zero because r must be positive. So 14 plus r must be greater than 0, and therefore we can cancel it out from both sides, and this will give us 14 plus r on the left side, and on the right side it will give us just 3r. So we get 14 plus r equal to 3r. Now this will give us 3r minus r equal to 14, correct? So 2r is equal to 14, or now finally r is equal to 14 by 2 or 7. So the length of AE and AF is 7 centimeters. And now finally we can find the length of AB and AC, which is what we really had to find. So AB is, as we saw, 8 plus R centimeters. So 8 plus R will be 15 centimeters because R is 7. And then AC is 6 plus R centimeters, and R is 7. So AC will be 13 centimeters. Okay, so these are the answers. AB is 15 centimeters and AC is 13 centimeters. So long solution, but very interesting problem. And to make sure that you've understood the solution, try working it out on your own once again without watching the video. Okay, so with this we complete question number. Question 13 of this exercise says, prove that opposite sides of a quadrilateral circumscribing a circle subtend supplementary angles at the center of the circle. So to understand what this problem is asking us to do, let's first draw a figure. So here's a circle that I'm going to use to draw my figure. And now I'm going to draw a quadrilateral that circumscribes this circle, which basically means that all the 4 sides of the quadrilateral should touch the circle and the circle should be inside the quadrilateral. So to draw any such quadrilateral is very easy. We just draw 4 tangents. So let's take our first tangent like this. Then let's take the second tangent to be like this. Then the third tangent, let me draw it here like this. And then finally the fourth tangent I'm going to draw like this. So now you see that we have a quadrilateral with these vertices. Let's call them A, B, C and D. So ABCD is a quadrilateral which circumscribes the circle. And let's suppose that the center of the circle is the point O. Now we have to prove that the opposite sides subtend supplementary angles at the center of the circle. So what does this mean? So let's take the side AB. So AB will subtend this angle AOB at the center of the circle, correct? Now the side opposite to AB is CD. So let's join OC and OD. So OC and OD, and CD therefore subtends this angle COD at the center. So we have to prove that these 2 angles are supplementary. In other words, we have to show that the sum of angle AOB and angle COD is equal to 180 degrees. So this is our problem. Now to solve this problem, here's what we're going to do. We are going to make use of the fact that OA bisects the angle at A. So this angle OAB and this angle OAD, these 2 angles will be equal. So let's call them angle 1, both of them as angle 1. Similarly, OB will bisect the angle at B. So we'll call both of these angle 2. Then OC will bisect the angle at C. So we'll call both of these angles angle 3. And then OD will bisect the angle at D. So we will call both of these angle 4. But why will this be true? Why will, for example, OA bisect the angle at A? Well, it's actually quite easy to show. If you take the points of contact of AB and AD with the circle. So let's take this point here, AB, where AB touches the circle as E and where AD touches the circle as F. And if you join OE and OF, then OE will be perpendicular to AB, so this angle will be 90, and OF will be perpendicular to AD, so this angle will be 90. And using this, it's very easy to show that triangle OAE, which is this triangle OAE, will be congruent to triangle OAF, which is this triangle OAF, right? And if these 2 triangles are congruent, then this angle OAE will be equal to OAF by CPCT. So I'm not going to show the full steps for proving these 2 triangles are congruent. We have done it often in the past, so you can do that. I'm directly going to make use of the fact that OA, OB OC and OD. They are respectively the bisectors of A, the angles at A, B, C and D. Okay, so let me write these observations. So basically what I'm saying is that OA bisects angle A, then OB bisects angle B, then OC bisects angle C, and then OD bisects angle D. Now if this question comes up on an exam, you can in your proof you can show one of these. You can, for example, show that OA bisects angle A, and you can then say that similarly all the other three statements will also follow. Alright, now the next step is to apply the angle sum property to the quadrilateral ABCD. Right, so in the quadrilateral ABCD, the sum of the four angles must be equal to 360 degrees. Right, so this is the angle sum property for quadrilaterals. Now what we're going to do is, for each of these angles, so for angle A, we are going to write angle A as twice of angle 1, because we can see that angle A is made up of two angles and both of them are equal, and we have taken both of them as angle 1. So angle A we can write as twice of angle 1, then angle B is twice of angle 2, angle C is twice of angle 3, and angle D is twice of angle 4. So this sum is equal to 360 degrees. And now if we divide by 2 on both sides, we will get angle 1 plus angle 2 plus angle 3 plus angle 4. This is equal to 180 degrees. Now this is very helpful, and you will see soon understand why calculating the sum of these four angles is helpful. Now we are going to apply the angle sum property to triangle OAB, which is this triangle OAB, and to triangle OCD. So OCD is this triangle. So we are going to apply the angle sum property to these two triangles. Okay, so by the angle sum property, and we are going to write expressions for angle AOB and angle COD. Right, so angle AOB we can write as 180 degrees minus the sum of the other two angles. So 180 degrees minus angle 1 plus angle 2. So note that in triangle OAB the other two angles are angle 1, which is this angle 1, and angle 2, correct? And similarly we can write a similar expression for angle COD. So angle COD is 180 degrees minus the sum of the other two angles. What are the other two angles in COD? Well, it's angle 3 and angle 4. Okay, so 180 degrees minus angle 3 plus angle 4. Now our proof requires us to show that angle AOB plus angle COD is 180 degrees. So now let's add these two equations. So let's label the various equations we have obtained so far. So this first equation, which is the sum of the four angles, let's call this equation 1, and let's call this equation 2, and this one let's call it equation 3. So I'm saying now let's add 2 and 3. Okay, so by 2 plus 3, what will we get by adding these two equations? So we will get AOB plus COD on the left side. So angle AOB plus angle COD. What will we get on the right side? So on the right side we will have 180 plus 180, so that's 360 degrees, minus, then we have minus angle 1 plus 2 and minus angle 3 plus 4. So basically minus angle 1 plus angle 2 plus angle 3 plus angle 4. Okay, and now the last step is simply to make use of the fact that angle 1 plus 2 plus 3 plus 4, this sum is equal to 180 degrees as shown in equation 1. So now we can therefore say that angle AOB plus angle COD is 360 minus 180 or 180. 180 degrees. So we have shown that angle AOB and angle COD are supplementary. Basically, this angle here AOB plus this angle here COD, these two angles we have shown they have a sum of 180 degrees, so they are supplementary. And similarly, we can claim that angle BOC, this angle, plus angle AOD, this angle, this will also be 180 degrees. So we can use a similar line of reasoning, or we can also make use of the fact that these four angles that are formed at O, at the point O, the four angles will have a sum of 360 degrees. And of those four angles, we have already shown that two of them have a sum of 180. So the remaining two, BOC and AOD, will also have a sum of 180 degrees. Okay, so with this we have proven that opposite sides of a quadrilateral circumscribing a circle subtend supplementary angles at the center. So this completes our proof for question number